Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. Today we will continue exploring angular momentum. First of all, we will prove that theorem that we talked about in the previous video relating the different systems of reference and angular momentum when the total momentum of the system is equal to 0. After that, we will relate torque to angular momentum for a single particle, and then we will expand this relationship to a system of particles. So let's start. Great. Consider that we have a system of particles. We'll denote this particle as the jth particle. Then we're going to have a system of reference, and we're going to have two axes, axis A and axis B. Our goal is to compute the angular momentum in A and relate it to the angular momentum with B and see if they are related. First, we need to express some very important vectors in this picture. We find that there is vector Aj, the analogous vector for B, or Bj, and the vector connecting A and B. Now, we know that LP equals the sum over J equals 1 to N, being N, the capital N, the maximum amount of particles that we have, of Rj cross Pj. Specifically, we would use Rb, J. Moreover, we know that LA equals the same thing. However, we observe from this vector triangle that Raj equals Rbj plus Rab. This expression. Therefore, we can substitute this in here and distribute the cross product, which is going to give us a very interesting result. So we have J equals 1 to N of Rb, J plus Rab cross Pj equals the sum from J equals 1 to N of Rbj cross Pj plus the sum from J equals 1 to N of Ra, B cross Pj. And now note two things. First of all, is that this expression is no other than this expression, so this is LB. And moreover, Rab is independent of the particle that we're examining. So we can use the distributive property of the cross product to put the sum inside of this part of the cross product, which gives us Rab cross the sum from J equals 1 to N of Pj, but that's no other thing than the total momentum of the system. So this is cross P system. And therefore, we observe that if Psys equals 0, which is the case when we're in the center of mass frame, basically by definition, then LA equals LB. And this is true for any A and any B. Therefore, we conclude, as we stated in the previous video, that when we're in the center of mass frame, or which is equivalent to the total momentum of the system that we're analyzing is 0, then the angular momentum is the same no matter the reference axis that we use to measure it. Right, now let's relate torque and angular momentum. Imagine that we have a particle here with mass m, velocity v, which is being applied a force F. Moreover, we have our axis S and the vector from this axis, or S. Now, we know that torque equals R cross F. And we would like to find a way to relate this quantity to our angular momentum, as some relationship between them could be really useful to solve different problems. Moreover, we also note that force equals the first derivative of the momentum by Newton's second law, the first time derivative specifically. Therefore, one thing that we could try and do is to take the derivative with respect to angular momentum, as we maybe expect some sort of relationship like this between torque and angular momentum. Therefore, we know that angular momentum equals R cross P. And if we take the time derivative of this gives us dl dt, and we have to distribute over the, not distribute, we have to apply the product rule, and we get that this is equal to dr dt cross p plus r cross dp dt. Then in here we recognize that this is r cross dp dt, which is f. So this is r cross f. Therefore, this term is no other thing than the torque. And this other term may seem complicated, however, we'll find that it's equal to 0. dr dt is no other thing than the velocity, and the momentum is no other thing than mass times velocity. Therefore, this is equal to mass velocity cross velocity, and we know that the cross product of two vectors that are parallel is equal to 0. So this goes to 0, and therefore this quantity over here is 0, which implies that the relationship that we found is torque equals dl dt. And this statement gives us the statement of conservation of angular momentum, which means that if an object has no torque applied to it, then its angular momentum doesn't change. Now let us generalize this to a system of particles. Imagine that we have, and let's denote this by its jth particle. Then we choose our reference axis to be over here, S, and we have the vector Rj. Moreover, this particle will have a momentum P of j, and it will have a torque applied to it. Then, if we want to calculate the relationship between angular momentum and torque, we need to carry out the same procedure that we did earlier, but we need to do some special things because this is a system of particles. Then consider the total momentum, angular momentum, that this object has, this system has. This is going to be the sum from j equals 1 to n of Rj cross Pj. Now, if we do the time derivative of this sum, we're going to find this is d dt of Ls, which in this case is gonna distribute all over the sum using the sum rule, and then it's gonna, using the product rule, we're gonna find that this is equal to the sum from j equals 1 to n of first drj dt cross pj, and then plus the sum from j equals 1 to n of rj cross dpj dt. Similarly as earlier, we find this is v, and the velocity is always parallel to the momentum as it's just a multiple of it. Therefore, we find that every single term on this sum is equal to 0, which gives us 0. And we also find that this term over here is no other thing than the force in the jth particle by Newton's second law, and therefore this entire thing is no other thing than the torque of that jth particle. Therefore, we find that total momentum is equal to the sum from j equals 1 n of dj. And now, here's where this special assumption comes, which is not really an assumption, it's a consequence of Newton's third law. This torque is going to be generated by an external force, if there is any, and by the different interactions among our particles, our system of particles. However, if this particle generates a torque on this particle in this direction, this other particle is going to generate in this particle the same magnitude of torque, but in the opposite direction, which will imply that opposite torques, like the pairs, the internal torques, will cancel each other. And therefore, this is just going to be the sum of the total torque that is being applied on the system with respect to S. The axis S. And sorry, because I forgot that this is ddt. Therefore, with this relationship, we generalize the previous relationship to systems of particles. That is all for today. I hope that you understood everything and got a sense of how we can generalize these statements to system of particles as we did in linear movements on our multi-particle systems videos. You have them over here. And you also got a sense of why, if the total momentum of the system is 0, the angular momentum is independent of the reference axis. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, subscribe to the channel and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!